Today, sophisticated equipment allows accurate predictions of extreme weather. High temperature. Italian physicist Galileo Galilei designed this thermoscope, early thermometer, about 400 years ago. A long tube with a bubble at the end sat in a flask of water. As the temperature rose, air in the bubble expanded, causing the water level in the tube to drop. As it became cooler, the air contracted and the water level rose. Flask would have been filled with water. A 19th century reproduction of Galileo's original thermoscope. Under pressure. In 1643, Italian physicist Evangelista Torricelli made the first barometer, a 3-foot, 1 meter long tube filled with mercury and put upside down in a bowl of mercury. The weight or pressure of air on the mercury in the bowl stopped the mercury in the tube from falling below 30 inches. Moving mercury. Meteorologist Robert Fitzroy invented this barometer, which has a scale to measure the mercury column. Fine weather is forecast when atmospheric pressure pushes the mercury column above 30 inches or 76 centimeters. Unsettled weather is predicted when it falls below this. A Fitzroy barometer. Invisible water. Air normally becomes humid, contains more water. Before a thunderstorm, the water in the air is an invisible vapor, but a hygrometer designed about 350 years ago is able to measure it. Water is absorbed from the air by the cotton bag, which becomes heavier. The greater the humidity, the more the bag drops down. This is a cotton bag for absorbing moisture in the air, balancing weight made of glass. It's a 17th century balancing hygrometer. Okay, weather glass. In this simple barometer, atmospheric pressure pushes down on the water in the sealed flask arm. The air inside the arm pushes in the other direction. As atmospheric pressure changes, the water level rises and falls. Before a storm, air pressure drops and the water rises up the arm. When working, the level of water in the weather glass would have been much higher than right here. When the water level in the spout is high, air pressure is low, and storms can be expected. So when the water goes up here, the air pressure is low, and the storms are probably expected. Hotness scale. You can pause it.
Go.
Hotness scale. When this thermometer was made in 1657, there was no agreed scale for reading measurements. Today, meteorologists use two main scales to record temperature, Celsius and Fahrenheit. Both scales were invented in the 18th century. Ornate thermometer made in Italy, 1657. A hottie, the spiraling tube of this glass thermometer saves space. When the temperature increases, water in the lower bulb expands, filling more of the spiral tube. The higher the water in the tube, the higher the temperature. Focused measurement. This glass ball focuses sunlight on paper. As the sun moves across the sky, the trail of scorches shows the amount of sunlight. If clouds hide the sun, there is not enough sunlight to scorch the paper. Sunshine recorder. That's what this is. These are the scorch marks on the paper. Imagine image of sun is reflected in the glass orb. Isn't that interesting? They used it to scorch the paper. Look at that. So those are when clouds came, where there's nothing there.
Whoa.
All right. An eye on the storm. Cyclonic winds spiral at their center, and so before hurricane radio warnings, sailors used this barocyclometer to measure changes in wind direction and atmospheric pressure. They could then work out which way the hurricane was moving and steer their vessels to safety. Thick needle aligns with the normal path of storms in the region. Thin needle indicates safe course away from the storm. It's a gas. During the 1770s, French chemist Antoine Lavoisier, I have never heard this guy's name, so I don't know how to say it, was the first person to discover that the atmosphere is a mixture of gases. He also found that hydrogen and oxygen combine to make water. What is extreme weather? For hurricanes and tornadoes, droughts and floods, to freezing and high temperatures, extreme weather can be dangerous. Weather can be described by wind speed, temperature, atmospheric pressure, and precipitation, rain, hail, or snow. The average world temperature is 59 degrees Fahrenheit or 15 degrees Celsius, but some places are colder or warmer. The average rainfall is 39 inches, 100 centimeters per year, but some places have no rain, others too much, and all at once. Extreme weather can happen where weather is usually calm. Dry places. The driest place in the Atacama Desert, Chile, which has had almost no rainfall since records began. Valley of the Moon in the Atacama Desert. The largest snowflakes were 15 inches. What? Across and fell in Fort Keogh, Montana, January 1887. Winds of up to 230 miles per hour or 370 kph at Mount Washington, New Hampshire, April 1934. Tornadoes. The atmospheric pressure in these rapidly spinning storms drops well below normal. The deadliest killed 689 people on March 18, 1925 in Missouri, Illinois, and Indiana. Mountain climates depend on the latitude and height. Areas with tropical climates have hot weather. Places with warm temperature climates have mild, wet winters and hot, dry summers. Places with a cool temperature climate have rainfall throughout the year, with warm summers and cold winters. Sliding snow. The fastest moving avalanche was in the Glarnisch Mountains, Switzerland in 1898. Snow sped down a mountain at 220 miles per hour or 350 kph. On August 13, 1849, a piece of ice 20 feet, 6 meters across fell from the sky in Scotland. What? Holy moly. Polar climates are cold, dry, and windy. This is a Russian Federation. The world's worst recorded flood occurred in 1887 when the Yellow River in China burst its banks, killing 6 million people? Man. Frozen. The coldest inhabited town in Verkhoyansk, Russia, winter temperatures can fall to negative 94 degrees or Fahrenheit, or negative 70 degrees Celsius. Tundra climates are cold with little rain and short summers. Storms between 1916 and 1919. 1919 is when your Meemaw was born. Naomi, their name. I think her name was Naomi Deck. Bogor in Java, Indonesia, had thunderstorms which occurred when hot, moist air rises for about 322 days each year. Hot stuff. In 1922, 136 degrees Fahrenheit, 58 degrees Celsius was recorded in the Sahara Desert, Libya, above, right there. But the reading was unconfirmed, and so the official record is 134 degrees Fahrenheit, 56.7 degrees Celsius, in Death Valley, California, in 1913. Heavy. The heaviest hailstone on record was a mass of 2.25 pounds, fell in Gopalganj, Bangladesh, in 1986. The hailstorm killed 92 people. Wow. In monsoon climates, the seasons change rapidly. Desert climates have less than 10 inches or 25 centimeters of rain per year. They're pointing to Australia. The tallest waterspout at 5,014 feet, 1,528 meters tall, was off the coast of New South Wales, Australia, May 16, 1898. Iced up Antarctic winds of 120 miles per hour, 190 kph, pick up snow and ice in the world's worst blizzards. Harsh conditions for these emperor penguin chicks.
Penguins!
Yes, I think I read everything on that. That was a lot of reading. Extreme causes. I think that's right. Important factors that affect the weather include the sun heating the earth and differences in atmospheric pressure. Dust from volcanoes and storms on the sun's surface can also make the weather hotter or colder and wetter or drier. Pollution in the atmosphere also affects the weather. Causes of extreme weather are understood, but predicting weather more than a few days ahead is still impossible because the weather is a complex and sensitive system. Spotting bad weather. Dark, cool patches can appear on the sun's surface for about a week. These sunspots throw out debris that sometimes reaches Earth. The spots are most numerous every 11 years, and extreme weather on Earth seems to coincide with this cycle, which we're heading into right now, I believe. Global warming. Many gases and smoke particles from modern industry hang in the air. This can impact the weather. Carbon dioxide from fossil fuels is contributing to an increase in the world's temperature. This global warming could upset weather balances, bringing more storms and rising sea levels. Chaotic weather. According to the chaos theory, this book kind of has the words in the gutter. The study of unpredictable systems, a butterfly can change the course of the weather. Weather is so sensitive to atmospheric conditions that a slight change in air movement, such as the flapping of a wing, can alter the course of the world's weather. How interesting! And we have all these wind farms. Deep depression. This barograph shows a depression, a common feature of unsettled weather over the British Isles. A depression is low atmospheric pressure. It forms when air is warmed, expands, and rises. Winds spiral in toward the center of the depression. The deeper the depression, the stronger the winds. Harmful gases. Chlorofluorocarbons, CFCs, are released by some industrial processes, and until the 1990s, when they were banned by aerosol cans. CFCs break down ozone, a gas in the Earth's atmosphere. Ozone protects the Earth from harmful ultraviolet radiation, like carbon dioxide. CFCs are known as greenhouse gases because they seem to slowly increase the world's temperature. Hot and cold. The sun is the Earth's main energy source. Sunlight hits the poles at an angle because of Earth's shape, and so the poles have less intense heat than at the equator. These temperature differences alter atmospheric pressure, causing global winds that influence weather patterns. Global cooling. Mount St. Helens in Washington erupted in 1980. For a few months after, there was a drop of 1 degree Fahrenheit or 0.5 degrees Celsius in the average global temperature because volcanic dust blocked some of the sun's heat and light. Sunlight warms the Earth. Sunlight is concentrated at the equator. Sunlight is spread over a greater area at the poles. Severe winds. Strong winds can wreak havoc. Their force depends on their speed. The fastest winds at ground level are in hurricanes and tornadoes. Higher in the atmosphere are even faster winds, jet streams, that help to distribute the sun's heat around the world. Global winds are caused by the sun heating parts of the Earth differently, while local winds are caused by regional changes in temperature and pressure. all at sea. In 1805, British naval commander Francis Beaufort devised a system for estimating wind speeds at sea. The Beaufort scale assigns names and numbers to 12 different strengths of wind. It is still used today. Standing tall, this model shows the 2,755-foot, 840-meter tall Millennium Tower proposed for Tokyo, Japan. An important feature for a skyscraper is wind resistance. This tower is encircled by a steel frame to strengthen it and protect it from winds. A weather vane. Weather vanes are perhaps the oldest meteorological instruments. This rooster's tail swings around as the wind changes direction and points the head toward the wind. A reading is taken of the direction from which the wind blows. Head faces in the direction from which the wind is blowing. This is called an architectural model of Millennium Tower, Tokyo. Wind swept. Wind and sand erosion can have carved these sandstone rocks. If severe winds blow across the rocks, sweeping up sand, dense and dangerous sandstorms can occur. Flying in the wind. In March 1999, balloonists Bertrand Piccard and Brian Jones became the first to fly a hot air balloon nonstop around the world. Their balloon, Breitling Orbiter 3, was sometimes assisted by jet stream winds blowing up to 185 miles per hour, 300 kph. God bless you. God bless you. Wind recorder. This anemometer records wind speed and direction over a period of time. To understand how the wind works, forecasters need to take as many measurements as possible. Weathered sandstone, Colorado Plateau, Utah. All right, this wind vane to show direction. Cups spin around. Their speed depends on wind strength. Rotors turn wind vane into the wind. Average wind speed is recorded as the cylinder rotates. So many things to think about, huh? A man struggles on Chicago's Wabash Avenue Bridge in fierce winds. The Windy City. Chicago is on Lake Michigan, where inland and lake air mix. The atmospheric pressure of these air masses is different, and so winds batter Chicago as they collide. Swing Bridge. Ooh, that is not good. Look at that. Strong gusts caused the Tacoma Narrows Bridge in Washington to swing. In 1940, eventually, the bridge collapsed. Since the winds were not hurricane strength, the bridge's design was blamed. Thunderous storms. Huge amounts of energy are released in the rain, winds, thunder, and lightning that accompanies thunderstorms. The most energetic storms create hail or tornadoes. The source of energy is the sun, which causes water to evaporate. The resulting warm, moist air rises and cools, creating a cumulonimbus. I am so sorry. I am having so much trouble reading all these words. Cumulonimbus cloud. The rising current of air, an updraft, may travel more than 60 miles per hour, 100 kph, when rain or hail falls. A downdraft of cooler air causes gusty winds. View from the air. This photograph, taken from a spacecraft orbiting Earth, shows how a system of storms can develop when cold, dry air undercuts warm, moist air, lifting it to form pockets of rising air. These pockets show up as thunderstorms. Water carrier. A thunderstorm is a towering cumulonimbus cloud. It may reach a height of 7.5 miles, 12 kilometers. While its base may loom just 3,300 feet, 1,000 meters above ground, it usually contains about 11,000 tons, 10,000 metric tons of water. Letting go. Tornadoes, lightning, and waterspouts often occur during severe storms as thunderclouds quickly release energy. Let's pause. Thank you. Can you pause it, please?
Ow.
Here, I'll pause it.
Oh, they hit the pause button. Go.
All right, we're going to do thunder. In Japan, Shinto religion, many forces of nature are worshipped as gods, known as kami. This kami of thunder is shown as a strong man beating his drum. Japanese thunder god. Thunder as a demon. Balls of thunder. Drumstick to beat out the sound of thunder. Interesting. Life of a storm. Hot, moist air rises, heavy rain and hail, cold runs out of energy. A thunderstorm develops when an updraft, red arrows of warm, moist air forms a cloud as the moisture evaporates from the air. Water vapor releases heat as it condenses. This heat warms the air more and causes it to rise higher. The storm subsides when the air cools and the downdraft, green arrows, disperses the cloud. All right, summer storms. Thunderstorms often occur after a hot day when air warmed by the ground rises quickly into cooling air. Dense thunderclouds absorb almost all the light that falls on them. This is why they appear black. Supercell storm cloud in Texas. Supercell. Most thunderstorms begin as cells, pockets of rising air. A supercell is a very large energetic cell in which air rises more quickly, carrying huge amounts of water into the cloud. Supercells create tornadoes and waterspouts. Strong updrafts carry wisps of cloud into the atmosphere, ice crystals, and water. Cloud stops rising and spreads as it hits a cold, dry layer of atmospheric air. Twisting tornadoes. Tornadoes have many names, including whirlwinds and twisters. These high-speed, spiraling winds leave a trail of destruction and are a bit of a mystery. They seem to develop at the base of thunderstorms as warm, moist air rises and passes through colder air. This draws winds that are already circulating in the storm into a high-speed whirl. The pressure at a tornado's center is lower than it is at the edges, creating a funnel that sucks up everything in its path. Here's a wall cloud. You were asking about a wall cloud. Are you pausing?
Yeah.
Did you pause it?
No.
All right, we're pausing. Ready? Here we are. We're at the wall cloud. They were asking about wall clouds, okay? These photographs show how a tornado develops. Its funnel descends from a thunderstorm. Its funnel descends from a thunderstorm above. A column of cloud then forms as moisture as the air condenses in the low pressure inside the tornado. So here's the tornado funnel appears at the base of a thunderstorm. So here is the wall cloud. It's a flat cloud. You were asking about it. It kind of has like a dent in on both sides and then it's flat. And that's where the tornado is going to form, in the wall cloud. Dusty debris. This tornado passes over dusty farmland. The base of the tornado is therefore obscured by dust picked up by the rising air and swirling winds. You see that? Funnel changes color as it picks up debris. Losing power. Energy from the tornado's winds throws debris into the air. As the tornado loses energy, it slows down. The funnel will then shrink back into the thunderstorm from which it was born. Funnel narrows as the tornado's energy diminishes. We used to watch tornadoes, like we would stand outside in Cashin and watch the tornadoes form and come down a little bit or go down all the way and come back up. And we would sit and watch Gary England on Channel 9, News 9 in Oklahoma, and watch Mr. Gary England talk all about the funnel cloud and where it was going and have the storm chasers out there. Liquid funnel. When a tornado passes over water, the updraft at its center sucks up water, forming a waterspout. A waterspout's wind speeds are much less than ordinary tornadoes because of the weight of the water it carries. Animal rain. Oh, that doesn't sound good. When a tornado passes over water, small animals may be lifted into the air, only to rain down once the tornado loses its energy. Spin cycle. The wreathing funnel of rapidly spinning air descends to the ground. from the base of a supercell at a tornado's heart. A low-pressure vortex acts like a huge vacuum cleaner, sucking up air and anything on the ground. Kicking up dust. Dust devils are common in desert regions, although less energetic and less destructive than tornadoes. They are created in the same way. The circling winds typically reach speeds of up to 25 miles per hour or 40 kph. What they didn't tell us, maybe they're going to tell us some over here. Tornado force. The swirling winds of a tornado are among the most destructive forces in nature. With speeds of up to 300 miles per hour or 500 kph, a violent tornado will destroy everything in its path. Most of the world's destructive tornadoes occur during summer in the American Midwest. Don't pull on my face, please. Where cold air from Canada, that's where a tornado hit. Where cold air from Canada in the north sits atop warm, moist air from the Gulf of Mexico to the south. This region is often called Tornado Alley. Where do we live? Tornado Alley!
We do?
Predicting where and when tornadoes will occur is extremely difficult. No, it's not. Tornado Alley. Stop. This map shows the area in the U.S. known as Tornado Alley, which includes parts of Kansas, Oklahoma, and Missouri. The region experiences several hundred tornadoes a year. Tornadoes claim about 100 lives each year in the U.S. A tornado rips apart a house, chasing storms. In the U.S., when a tornado watch warning is issued, storm chasers pursue tornadoes to learn more about them. Circles of mystery. For centuries, unexplained circles of flattened crops have appeared in fields across the world. Some people believe that tornadoes are responsible, but this is unlikely since tornadoes do not hover over one spot for long enough. Strange tales. A chicken in Alabama is reported to have survived tornado winds of up to 125 miles per hour, 200 kph, which stripped it of its tail feathers.
A chicken survived?
It says it did. 125 mile per hour winds. Areas most at risk for tornadoes are in this stripy orange lines. Twisting column of cloud, swirling vortex, dust and debris are swept up as the tornado moves along. Towering. The destructive vortex spinning center of a tornado is usually about 1 mile wide. Woo! Dust, or 2 kilometers wide. Dust or objects at ground level are lifted high into the air and flung sideways or kept in the air and deposited when the tornado winds down. Tornadoes typically travel at 35 miles per hour. Stop, son. 55 kph. Maverick, I'm reading. Please stop. Venetian blinds twisted by a tornado. This is a broken window. So these are the kind of vines. Venetian blinds. They're just all twisted up. Look, it's crazy. Blind panic. Much of a tornado's destruction is caused by the sudden drop in pressure that it brings. This wind exploded outward when a tornado went by because air pressure inside the room was higher than outside. Door sucked out of a window by the tornado's force. See, look at that. The door to the bedroom. It's crazy. Blown away. In March 1994, a tornado ripped the roof off this church in Piedmont, Virginia, surprising the congregation during a service. Holy moly, there are people in there. In a twist, tornado winds traveling at more than 250 miles per hour, 400 kph, picked up this truck and hurled it down again, leaving behind a mess of twisted steel and showing the incredible power of a tornado. You see that truck? You can't tell it's a truck. Measuring tornadoes. Meteorologists use an anemometer to measure wind speeds accurately, but getting one inside a tornado is dangerous, and because tornadoes move, it is difficult to get accurate readings. Previously, meteorologists categorized tornadoes based on estimated wind speed and damage caused. Today, though, the Doppler weather radar actually accurately measures wind speeds inside a tornado. Doppler on wheels. Doppler radar mounted on a truck to get close to the tornado measures wind speed in a tornado without equipment breaking or anyone getting hurt. Microwaves directed at the tornado's edge bounce off water droplets carried by the wind. Computers in the truck then determine the speed at which the droplets are moving. Path of a tornado. Most tornadoes travel at 20 to 50 miles per hour, 30 to 80 kph. This image shows the path of destruction left by a tornado in Oklahoma in 1999. It was like a horrible tornado in Moore, Oklahoma. It had the longest path and it was super wide. I believe that's the one they're trying to show here. It was very sad. Radar dish sends out and receives microwaves. All right, let's see what's over here. Tetsuya Ted Fuhata. Can't say that right. Sorry, guys. 1920 to 1998. In 1971, this severe weather expert designed the Fahrenheit scale. I didn't realize it was that recent, which categorized tornado. Oh, sorry, the F scale, not Fahrenheit. Why did I say that? Oh my gosh. The F scale, which categorized tornadoes based on the damage they cause. Today, most countries use the enhanced Fujita scale, EF scale. I only know it as the F scale. I don't know how to say his name. Meteorologists in Britain use the Toro or T scale. Portable Toto, now defunct. The Totable, meaning portable, Tornado Observatory, Toto, was a metal drum containing instruments that could be placed in the path of an oncoming tornado. It was deployed several times unsuccessfully after being blown over by a moderate tornado. Toto was retired. Enhanced F scale. Meteorologists in the U.S. and Canada began using the enhanced F scale, EF scale, which runs from EF0 to EF5. In 2007, several other countries also use it. It gives more accurate wind speed estimates. EF0, minor damage, the 65 to 85 mile per hour, 105 to 137 kph winds can uproot shallow-rooted trees and damage chimneys. EF1, moderate damage, winds of 86 to 110 miles per hour, 138 to 177 kph, overturn mobile homes and damage roofs and windows. EF2, considerable damage. The 111 to 135 mile per hour, 178 to 217 kph winds can tear off roofs, uproot large trees, and lift cars off the ground. EF3, severe damage. Intense, 135 to 165 mile per hour, 218 to 266 kph winds. Damage well-constructed buildings and can overturn trains. EF4, devastating damage. Wind speeds of 166 to 200 mile per hour, 267 to 322 kph can ruin houses and lift cars, blowing them long distances. An EF5, incredible damage. Wind speeds of more than 200 mile per hour, 322 kph are very rare, but are able to detach houses from their foundations.
That's very high.
Yeah.
Strong, very strong.
All right, Izzy, I think we're going to stop there for our part 1. We'll start part 2 with lightning strikes.